Yo, what's up, everyone? Welcome to Kinetics Part 4. Today we're going to go over catalysis. And so what is catalysis? According to some dictionary online, catalysis is the modification of the reaction of a reaction, usually an acceleration by addition of a substance not consumed during the reaction. And so those substances, are the way how catalysis works is through catalysts. To kind of explain why catalysts, before we get into catalysts, I kind of want to give you an analogy for why catalysts are so important. And so imagine you're this red dot right here, and you want to get to the blue dot, and you can only go through the white lines. Now, a certain pathway that you could go through is you can go up and then to the right and then back down. And I mean, if you look at this diagram for any more than 10 seconds, you'll realize that that's not the most optimal route. If you had Google Maps with you, Google Maps would probably tell you that you would just want to do a straight line, and that would be the simplest path to get there. Catalysts do kind of a similar thing. Catalyst is a substance that increases the rate of a reaction. So the pathway that something might take from A plus B to C without a catalyst is like this. It might go all the way up here and then go all the way back down. So you can kind of see how the activation energy is kind of high with an uncatalyzed reaction. But if your reaction was catalyzed, you might have something like this. You can see how it's taking a different pathway. And this pathway looks a lot more complicated, but you'll realize that the activation energy is overall less. The activation energy is like here as opposed to all the way over here in the uncatalyzed reaction. And you can see kind of here how the activation energy has decreased. So this definition of a catalyst is almost incorrect. It's not really a substance that increases the rate of reaction. It's a substance that decreases the activation energy. And since the activation energy is decreased, that in turn increases the rate of a reaction. An important thing about catalysts is that they don't change the change in enthalpy that occurs between the reactants and the products. You can see that the change in enthalpy is that in the uncatalyzed reaction, and it's the same thing in the catalyzed reaction. So really, catalysts lower the activation energy by altering the reaction mechanism. And this is important because that means that catalysts can change the elementary reactions. And as such, catalysts can change the rate law. Alright, let's back up a little and talk a bit about what they look like in a reaction. So if you have the reaction A plus B to C and then C plus D to D plus E, well, you can see the B here is used up in one reaction and then reformed in another reaction. The B in this case is the catalyst. And so catalysts are used up in one reaction and then reformed in a subsequent one. This is really important because this tells us that a single molecule of a catalyst can work in many reactions before getting used up. They are not used up in a singular reaction, and that's what makes them so useful. And so again, catalysts are not used up in a reaction. Another thing about catalysts is that they do not affect equilibrium. So catalysts affect the forward reaction and reverse reaction by the same factor. So if you double the forward reaction, the reverse reaction would also double. And doing that, it does not affect equilibrium or like the position of equilibrium. Rather, it changes how fast the reaction will reach equilibrium. Another thing is that there's going to be two types of catalysts. First is going to be homogeneous, so these are going to be catalysts that function in the same phase as the reactants. And it's going to be heterogeneous, so catalysts that function at different phases from the reactants. Alright, I think that's all the lesson bit. Let's just do a bit of practice to solidify all this. So a reaction takes place by an uncatalyzed pathway whose reaction coordinate diagram is shown below. And so it's this one right here. Sorry, my pen just stops working sometimes. This one right here, that's going to be the uncatalyzed reaction. And so the reaction is accelerated by addition of a small amount of a catalyst, which reaction coordinate diagram best describes the catalyzed reaction. So the two things that we can take out right away are A and B. A, you can see, is the exact same as the uncatalyzed reaction, which doesn't make sense. The catalyzed reaction is going to have some change to the pathway that the reaction takes. And B is also incorrect because you can kind of see how the activation energy has increased in B. And remember, the activation energy decreases in catalyzed reactions. So A and B are incorrect. If we look at D right here, the D does something completely weird. D goes all the way down here. And that doesn't make sense because a reaction wouldn't go from intermediate to products if the intermediate is at a lower level. And so the only thing that makes sense really is C. And you can see how C kind of makes sense because we're taking a different pathway. You can see how there's going to be more intermediates in this case, but also the activation energy has decreased. It's over here now, and that's going to be the EA, which is lower than the activation energy over here. So therefore, our answer is going to be C, which is the correct answer. Let's move on to the next one. In which of the following ways may a catalyst increase the rate of a reaction? 1, it may alter the rate law, and it may decrease the overall activation energy. Well, number 2 is going to obviously make sense. That's what we've been talking about this entire time. Catalysts change or decrease the overall activation energy. So 2 makes sense. And 1 also makes sense because remember, catalysts change the reaction mechanism. And so that means that they can also change the elementary steps. And the elementary steps are going to have a major impact on the rate law itself. So number 1 also makes sense. So the answer here would be C, which is in fact the right answer. Let's move on to, I think this is our second to last one. The graph below shows the forward and reverse rates for a reaction as a function of time. At time t, a catalyst is added to the system, and the forward reaction rate is observed to change as indicated by the solid curve. Which dashed curve best indicates how the reverse reaction rate changes? Well, we can see how the forward reaction doubles. It goes from here to here. And so if the forward reaction kind of doubles, then the reverse reaction would also have to double. So if the forward and the reverse reactions are at the same position and a catalyst is introduced, then they're going to end up at the same position. So really the reverse reaction would also end up at the A position here. And so our answer in this case would be A, which is the right answer. So again, catalysts do not change equilibrium. They affect the forward reaction and the reverse reaction by the same factor. And therefore, they only change how fast equilibrium is reached. Let's move on to our last problem, which says hydrogen peroxide decomposes into water and oxygen. By a small amount, adding a small amount of FeCl3 increases the rate of gas evolution in this reaction. What is the best description of the role of FeCl3? Well, I mean, we've talked about this whole time, and since FeCl3 increases the rate of gas evolution, we know that it's going to be a catalyst. But you can kind of see how there's 2 answer choices that say catalyst, heterogeneous and homogeneous. And so which one would it be? Well, our reactant here would be hydrogen peroxide, so H2O2. And the important thing about this is that it's in the aqueous state. Now the catalyst, FeCl3, is also in the aqueous form. And remember, if we have if the catalyst is in the same phase as the reactant, we say that it's going to be a homogeneous catalyst. And so our answer choice is D. Heterogeneous means that it would be at a different state, which in this case it is not. So our answer here would be D, which is the right answer. All right, that's all I have for this lesson. I hope you learned something, and I'll see you later. Thank you.